All right, Honors Chem, we are going to start a new unit today. It is states of matter, otherwise known as the kinetic molecular theory. So you have done a lot of this already, probably in 7th and 8th grade. What makes a solid? What makes a liquid, and what makes a gas a gas? So we're going to talk about it on a little bit deeper level this year, and hopefully you'll really be able to understand why things are the way they are and why they act the way they are based on the molecular level. So here we go. Today we're going to talk about states of matter, solid, liquid, gases. But first we're going to dive into the kinetic molecular theory. Okay? So the kinetic molecular theory has a basic premise. And that basic premise is that all matter is made of particles that are in motion. All matter is made or consists of particles that are in motion. Okay? Now, we take the name kinetic from the Greek. If you look at Greek, kinetics means motion. So we're thinking about molecules or atoms or ions that are in motion. Okay? So here are the main ideas of the kinetic molecular theory. Now, these postulates or these ideas are mostly in terms of gases. Let's rewrite that. Now, these do apply somewhat to solids and liquids, but not all of them. But they definitely do apply to the idea of what we think of as an ideal gas. So this is what we think of as an ideal gas. Things that follow the rules or the laws. Okay. So here are our postulates or our main ideas that we're basing this theory on. Postulate 1, all matter is composed of small particles, and those particles can be molecules, ions, or atoms. Okay, that's not really earth-shattering. Number 2, molecules of gas are separated from their neighbors by distances much greater than the size of the individual molecules, meaning that if I have a molecule here and a molecule here, the distance here between these two molecules is much bigger than the size of the individual molecules, meaning that gases are mostly empty space. Number 3, the volume of individual molecules is so small as to be considered insignificant. So if I took a room full of air and I compressed it down so that the molecules were actually touching each other, the size of the molecule volume would be so small compared to the volume of the room that the air occupies that we consider the size of the volume of the molecules in and of themselves to be insignificant. Okay? Number 4, particles, these gas particles or molecules are in constant random straight line motion until they collide with other particles or walls of their container. Now, you've seen this random straight line motion if you've ever played air hockey or if you've ever seen a hockey game right after the ice has been Zamboni'd really well. So on an air hockey table, if you hit that puck, it glides across that table and it stays in straight line motion until it hits the side of the hockey table or your opponent hits it back at you. It stays in a straight line motion until it hits something. That's what we're talking about. Number 5, the collisions are elastic, which means that there is no change in total kinetic energy, the energy of the motion, speed, and mass. There's no change in that kinetic energy of the two particles before or after that they collide. So the energy into the collision equals the energy out of the collision, which means that the velocity that the molecule is traveling in before it hits is going to be the same as the velocity after the molecule is done with the collision. Okay, we don't lose any energy. Number 6, the average kinetic energy is the same for all molecules at the same temperature. Now, this is the key for this. average, do individual molecules have different kinetic energies? Yes. But when we average them all in, if anything is at the same temperature, it's going to have the same average kinetic energy. So that means, like, for example, in this cup that I have, because all these pens and markers are at the same temperature because they've been sitting in this room, the average kinetic energy in this yellow pen is going to be the same kinetic energy of the molecules in the pencil is going to be the same kinetic energy that is found in the molecules making up this cup. Okay? All right. And then kinetic energy is directly proportional to the temperature in Kelvin. Now, we have not introduced the Kelvin scale. The Kelvin scale is based on absolute zero. Okay, so absolute zero is the idea that if I get cold enough to get to absolute zero, all kinetic energy, all motion of all molecules stops. That's where all motion stops. Okay, so this is where all molecular motion stops. There's no kinetic energy at all. Zero kinetic energy. So if we put that on the Celsius scale, 0 Kelvin is equal to negative 273 degrees Celsius. Now notice when we do Kelvin, we do not put this little degree or this little O naught on there. It's just Kelvin. Okay? So let's talk about gases really quick. And let's list some properties of gases. Now, gases, when we think about gases, we know that those molecules can go past one another. They are not held in a rigid crystalline structure. We see this all the time when we're outside and the wind's blowing or we blow on something. Those molecules can flow past each other. So molecules in gases flow. That means they can move past each other. Okay? And because they can flow, that means that gases have no definite shape and no definite volume. Okay? So because they have no definite volume, they occupy the volume of their entire container. Okay? No definite volume. Okay? And they also take the shape of their container. Takes the shape of their container. So no definite shape. Okay? Very low density. Okay? Very low density. Okay, mostly empty space. And because it's mostly empty space, gases are easily compressible. I can smush the molecules closer together, or expandable. I can do that really easily. Let's show you this diagram. In this diagram, I have a piston that I can move up and down. If I move this piston down, I can compress the gases so that they're closer together. Or if I move this piston up, I can expand the gases and they're going to be further and further apart. We use this compression and expansion, especially in the internal combustion engine, when we burn gas and that gas explodes into gases instead of the liquid gasoline, and that explosion expands that cylinder really far with some force and turns the crank on our internal combustion engines. We use that all the time to drive our cars. Okay, so here we go. Gas pressure. Gas particles exert pressure when they collide with the walls of their container. You've seen this when you blow up a balloon, right? You've got the pressure of the balloon expanding the more gas you put in there. Because individual gas particles have so little mass, it can exert very little pressure. However, a liter-sized container, like a liter, like about this, can hold 10 to the 22 gas particles, so almost a mole. With this many particles colliding, the pressure can be pretty high. Okay, air pressure. Earth is surrounded by an atmosphere that extends into space for hundreds of kilometers. Okay, most of the atmosphere is about 10 kilometers down, about 90% of it. But when you get to 100% of the atmosphere, it can go to about 200 kilometers above. Because the particles in the air move in every direction, right? Random straight line motion, every direction, they exert pressure in all directions. This pressure is called atmospheric pressure or air pressure. Air pressure varies at different points on the Earth because gravity is greater at the surface of the Earth, and also because there are more particles than at higher altitudes. Just think here in Salt Lake City, we have about 4,500 feet less of atmosphere on top of us than somebody at sea level. So we have 4,500 feet less of air molecules pushing down on us. So the air pressure that we have here in Salt Lake City is going to be less than somebody who's living at sea level. Okay? Hopefully you've felt that when you've traveled places. Have you gone to sea level and you find it a lot easier to run and do exercise? And then you come back after a week or two and your body has adjusted to sea level and it becomes really difficult to breathe here because there's less oxygen? Yep. Okay. So let's start back right here. Fewer particles at higher elevations exert less force than greater concentration of particles at lower sea levels or lower altitudes. Therefore, air pressure is less at higher altitudes than it is at sea levels. Okay, so let's look and see how a barometer works. So this is a really simple mock-up of how a barometer works. Barometers were invented by the Italian scientist Torricelli. Okay, barometer is an instrument that we use to measure atmospheric pressure, and we use barometers very much to measure weather patterns. You'll notice when we have high sunny days, we have high atmospheric pressure. We have a lot of air coming down and creating a lot of pressure. And that's where we have our bright, sunny days. And if we have a low pressure, that means that the airstream is mostly rising up and we will have stormy, unsettled weather. Okay? Sea level, the height of mercury in a barometer is 760 millimeters of mercury. And let me tell you how we get that 760 millimeters of mercury. Torricelli created a pan of mercury, and he used mercury because it was very dense and it didn't really evaporate, so it would stay there. And then he put a tube with markers or measurements on it that had been vacuum, so it had no air, it had nothing in it. And he noticed that if he inverted that tube into this pan of mercury, that some of the mercury would rise up into the tube. And it would rise up because the air pressure is pushing down on that mercury. So we can measure the height of that column of mercury in that tube with the markings and understand how much pressure the atmosphere is actually pushing down on us. So when we do that at sea level, we get a measurement of 760 millimeters of mercury, almost three quarters of a meter, pretty high. Okay. So in Salt Lake City, because we don't have as much atmosphere pushing down on us, normal atmospheric pressure in Salt Lake City is about 645 millimeters of mercury. Okay, you'll notice that our pressure is significantly less than at sea level. Now, there's something special about this sea level pressure. This 760 millimeters of mercury is what we call standard pressure. Okay, so that is standard pressure. Okay, and we will use standard pressure. Sometimes it's called normal pressure. So standard or normal is something that we use all the time, especially when we're using gas laws. And if we have time at the end of the year, I'd like to do gas laws, but we'll see if we have time. Okay, so I talked about the postulates being something that we think of as an ideal gas. I want to talk about what is different between an ideal gas and a real gas. Okay, so an ideal gas, the molecules are not attracted to each other at all. Okay, molecules are not attracted to each other. Okay, that because the lack of attraction, that makes it so that all those collisions are elastic, just like our postulates say. But do real gases behave like that? No, we have things called intermolecular forces. Remember our polar molecules where we have some side that's positive and some side that's negative? They're going to line up together and they're going to attract each other like little magnets. So real gases actually have attractive forces, okay? So real gases actually have attractive forces. And we will talk about those forces of attraction in a little bit. They're called IMFs, intermolecular forces. Some are quite weak, some are quite strong. Okay? So if we want gases to behave ideally and not have attractive forces, what kind of temperature are we going to have, and what kind of pressure system are we going to have? Think about that for a minute. What's going to make these molecules not attract to each other and not react or attract each other? The temperature is going to have to be really high so those molecules are moving super fast so that when they do collide, they collide hard and they bounce off of each other. So we're going to have really high temperatures. What kind of pressure? Am I going to want to have pressure where it's all smushed together, lots of pressure, or am I going to have less pressure so that they're expanding out? Yeah, we're going to have very low pressure. I want things to be expanded out so the molecules are going to be really far away from each other. Okay? So, what happens to a gas when the opposite occurs? When I have low temperature and I have high pressure. Low temperature means that those molecules are going to be moving really slowly, and high pressure means that those molecules are going to be smushed together, really close to each other. If I have molecules that are moving slowly and they're close together, that means the gas will those molecules are going to glom onto each other, and I will actually liquefy the gas. The gas will liquefy. And condense. That's condensation. Condense. Let's not do condensation, let's do condense. Okay? So here's a little diagram that gives you the difference between gases and liquids. Notice there is a lot of space between the molecules in the gas. Granted, you can't really see molecules. And in a liquid, the molecules are pretty close together, but notice there is no strict arrangement of how those liquid molecules are. Okay, let's talk about properties of liquids. Okay, can the molecules in a liquid move past each other? Yes, so that means that the liquids can flow. Liquids can flow, molecules can move past each other. Okay. Do molecules take the shape of their container in a liquid? Yes, they do. Molecules take the shape of their container. That means there is no definite shape. Do molecules in a gas or in a liquid take the volume of their container? No, they don't. I can still have a container that's half full of water or half full of milk or half full of oil, okay? They have a definite volume. So liquids have a definite volume. Because the molecules are close together, there is a volume. They will not expand to take the whole volume of their container. And because those molecules are close together, liquids are incompressible. We might be able to compress them really a very small bit, but essentially the molecules are next to each other, so they're incompressible. All right, how many of you guys have used surface tension before? Okay, we've all seen those penny skippers across the water, right? The surface of the water actually holds together because the polarity of the water molecule, and it creates kind of a surface tension, a tension of molecules that will hold tight to each other so that these animals and the leaves and things that we have will float on top of the water, okay? So surface tension is basically the energy required to increase the surface area of a liquid. Okay? Due to intermolecular forces. And there's that IMF again, intermolecular forces, okay? The stronger the surface tension, the stronger the intermolecular forces are, okay? You've probably seen this. If you've ever played with acetone or alcohol, that evaporates really quickly off of your skin. It makes it cold. If you spread it out, it spreads out in a really thin layer. But if you do that with water, water kind of has this bubble quality to it, and it stays on your hand longer because it has higher surface tension. Those molecules in water are more polar, therefore they're going to stick together stronger. Okay? Let's talk about viscosity. Viscosity is the resistance to flow. Okay? So think about things that really flow slowly. Think about the difference of pouring water out of a jar versus honey. Which one is more viscous? Honey definitely is. Honey does not like to flow. In fact, sometimes you have to heat the honey up so that it will flow. If you get a jar of cold honey, even if it hasn't crystallized yet, it won't flow if it's cold. Okay? All right, let's talk about solids really quick. Solids and their properties. Solids don't flow. Okay? Those molecules are stuck inside a crystalline structure. The molecules just vibrate back and forth. Just really, really about a fixed point. They can't flow, okay? Do not flow, okay? Those molecules vibrate about a fixed point. We have kind of a crystalline structure. Okay? Solids have a fixed volume or a definite volume. If I put a chunk of coal in my bowl, it's going to stay a chunk of coal. It's not going to take the shape of my bowl. And they also have a definite shape, right? That do not floor gives us a definite shape. Okay? And they are incompressible. I cannot smush the molecules closer together in a solid at all. They're next to each other as much as possible. Okay? So they have a definite volume. They take the shape of their container. They do not flow at all. Okay, so there's a little introduction into solids, liquids, and gases. Next time, we will talk about these forces of attraction and learn what the different intermolecular forces are, and you'll be well versed in IMFs. Talk to you later. Bye.